Okay, so any questions from last time? No? Okay, so just a short talk or lecture talk today. And what we want to think about now are basically just what are called discrete probability distributions. Okay, discrete probability distributions. And what we'll find is that they are actually associated to random variables. So remember, we started with talking about events, right? It's the outcome of a random experiment. And then you have this random variable that associates some kind of a number, like the number of heads. Or if it's the roll of a die, it's the value that shows up, 1, 2, 3, 4. So anyway, 5, 6, associating some kind of a number to events. And then we also looked at probabilities on events. Now we want to look at basically probabilities on the random variables, on the values of the random variable. Okay, and we're basically somewhere between section 1 and section 2 of 5.1 and 5.2 in the book. Okay, so what are some of the main concepts from last week, right? And last week we were looking at events, right? The probability of A or B is one of the main topics, and this probability of A and B, right? So in symbols, how would we do OR? How do you handle OR? OR is with that union. Yeah, people are drawing that, right? So that would be the probability of A or B, union, right? And so the main concept about union or is basically you want to add, right? And we had that general formula, right? There's a probability of A plus the probability of B, and then can you stop there, right? In general, the answer is no, right? Because there could be some intersection between A and B. So when you add probability of A, that includes the intersection with B, and then when you include this probability of B, that also includes the intersection with A, and so you actually have this intersection there twice, and so you have to make sure that you subtract one copy of it and leave one copy back. Okay, and then probability of A and B, right? We said that some authors, including our book, have this upside down one of those, right? It looks like that. And some authors actually just leave out the and symbol. And so sometimes if you read articles or you look at some books and you see this AB, then you should assume, and it's talking about sets or events, then you should assume that it's intersection. And what's the main concept about intersection? So I guess we should say here it's generally bigger, add to get bigger, right? The intersection is smaller, right? Because it's in general, right? It's smaller. And how do you make it smaller? You multiply, right? Minusing would do it, but minusing is kind of like the opposite of adding. If you take, remember probabilities are fractions, they're all less than 1. So if you take any number and you multiply it by a fraction, by a number less than 1, it gets smaller, right? And so what we want to think about is when we do intersection, which is smaller, we multiply. Okay, and then the general formula, right, was that the intersection would equal to say P times the probability of A, equals the probability of A times the probability of B given A, which is actually the same thing as the probability of B times the probability of A given B, right? And so when, in order, I mean, we were kind of wanting to deal with this intersection, but the way we got it was we did this conditioning thing, because when you do the conditioning formula, it's this intersection divided by the total probability. So it's intersection divided by this total probability, right? So the probability of A given B would be this intersection divided by the probability of B, and this probability of B given A would be the probability of the intersection divided by the probability of A. And so remember, that's kind of how we got it. But the reason why, one of the main reasons why we were looking at this conditional stuff is to kind of get that the intersection and is multiplying. Okay? And now it turns out that, you know, a lot of times when you hear about special cases, you think, oh, you know, that's like a special case and it doesn't happen that often, so you kind of like maybe push it out of your mind and you want to remember the general case. So it turns out that when we do the distribution, we are actually in the two special cases, right? So remember, if we're doing OR, right, one of the special cases, do you remember the special case, what we call that, the special case for OR? When does this formula become a little bit simpler, right? The formula becomes simpler if we can just do probability of A plus the probability of B, right? And then for and, right, it's possible in some cases where it's just the probability of A times the probability of B. Okay, those are the two special cases. And it turns out where we're going into distributions is distributions have both of these special cases. Okay, so that's kind of why we did stuff last week in order to understand that it is possible to add probabilities. You don't always have to have this correction, and it is possible to get the and by multiplying probabilities. You do not always have to find this conditional piece. So what were the two special cases? You can just, for or A or B, you can just do this add and not worry about this intersection when the two events are right, mutually exclusive. Okay, and when you have and or intersection, you can get away with just multiplying by probability of A times the probability of B when A and B are, starts with I, right? Independent. Okay, and so as I mentioned, a lot of times you think, oh, those are special cases, and you know we may not have these special cases. Actually, these it's makes life so much easier when you can just add probabilities and not have to worry about the intersection, and when you can just multiply probabilities and have them be independent. And so that's actually what we will assume as we're using the distributions, okay, as we go to probability distributions. Okay, so let's kind of remind ourselves, right? Draw a Venn diagram and a contingency table for the case where events A and B are mutually exclusive. So what does it look like, right? So if we're doing the Venn diagram, right, we of course kind of might start with our universe, Venn diagram. And then of course the contingency table looks a little bit like a window, right? So we might start with that. And usually when you draw the Venn diagram, you have the overlapping circles, right? And there's a section that looks like a football maybe, right? But if A and B are mutually exclusive, what happens? It means there's no intersection, right? So how can we draw that, right? We can just draw this circle like that, right? So this would be A, and this would be B. And in particular, the mutually exclusive, right, means there's no intersection, right? So maybe we'll just try to make a note of that. Intersection, maybe I'll just say A intersect B is equal to the empty set. So that's sort of a shorthand way of saying the intersection between A and B is empty. There's nothing in the intersection. They don't overlap. There's no intersection, right? So this is sort of a very compact way to say there's no intersection. And you can see, right? So when we add all of A and all of B together, there's no extra little bit of intersection that we have to subtract out. Okay? And then, you know, we might have some amount over there. And so this x could be 0 or could be other stuff. Okay? So it doesn't matter if you do A on the vertical side or B on the vertical side. You just do B and B complement or not B on the other side. And so clearly, since A and B have no intersection, right? They're empty, right? And so all of the A stuff is here. No, sorry. All of the A stuff is here, right? And then all of the B stuff is here. And then we might have some extra little bit of stuff over there, right? So the A stuff would basically be, say, A. The not A stuff would be possibly B and X. And remember, X could be nothing or it could be something, could be nothing. And then the B, right, would be all of this stuff. So it would be B. And the not B, what's not B, would be basically A and possibly X. And then this total would be A, B, and if X is something, then we would include that together in this sort of total, grand total, right? So these would be the row totals, right? These would be the column totals, and then we might call this the grand total of everything. Okay, so notice down here, what is this a picture of? So this Venn diagram and this contingency table are related, and what is it showing? Sorry? Right, it's showing an intersection. And so remember, we're trying to look at, you know, what's mutually exclusive and what's independent. So this pair up here was mutually exclusive, and so the Venn diagram and the contingency table down there are independent, right? Thanks. So you may be saying, so I don't see the independence, right? So it's a little bit harder to see the independence in the Venn diagram, but if you look here, right? So what does it mean for independence, right? So it would be, say, the probability of, say, H3 given H12, right, equals the probability of H3. Okay. So in order to look at the contingency table, you look at the contingency table and you say, well, I don't see where it's independent, right? So here's how you notice, right? Remember that this is what independence means, right? So what's the probability of H3? Right? So here you have to look at the probability of H3. Right? So the probability of H3, right, is basically 4 over 8 which is equal to a half. Right, so here it may be easier to see H3. So what does it mean for H3 means that the third, so this is like 3 tosses of a coin, right? And so the probability that the third one is heads is this set. So there's 4 of them, okay? And then we know that the total has 8. So the probability of H3 is 4/8, or 1/2. Okay. So what's the probability of H3 given that H12 has happened, right? So given that H12 has happened, right? In fact, not H12 has not happened. So given that H12 has happened, given that this has happened, what's the probability of H3? Right? So here it's probability of H3 is 1 out of 2. Right? So you can see that the direct way is 1 out of 2. If you want to look at the Venn diagram is saying H12 has happened. So now this is our square, actually, right? All the other cases we sort of throw away, and this is our new universe. And then what's the probability of H3? So H3 would just be this 1 out of this 2. Okay, so it's a little bit easier to see here where, you know, this total probability, you look at the column, so 4/8, whereas given that H12 this is the new reality. Given that H12 has happened, we're given that H12, what's the probability of H3? So then it's 1 out of 2, it's 1/2. So if this sort of lines up with this, then it's independent. And notice that we could also do this way, right? 1 out of 4 is the same as the grand 2 out of 8. Okay, because 2 out of 8 is 1/4. Okay, so if you see the contingency table, you look at this, and this as one sort of ratio, and you look at this, and this, and you say, hey, that's the same ratio. And then just to check, you can look this way, and then you look at the row total. Look at one row, the first row, and you look at the row total, and you say, hey, it's the same proportionately. So this is what independence looks like. Okay, and you can see that independence and mutually exclusive are different, right? Because mutually exclusive means this one is 0. So this case is independent but not mutually exclusive. And so you could have the case where we are going to see the case where it's mutually exclusive and independent. Right? Anyway, okay. So remember what we were talking about is how do we or what is a random variable, right? A random variable is any method to assign a number to the outcome, or a unique number to each outcome. So here it's okay because this outcome has a unique number, this outcome has a unique number. It's okay if some of the numbers are repeated, right? So one random variable could be counts a number of heads in 2 tosses of a coin. So this we might say x2, capital X for a random variable, right? Here, if there are 3 tosses of a coin, x3 could be the number of heads in 3 tosses of a coin. Okay? And so you can see that when we talk about random variables, we use capital letters to be the value itself. Oh, sorry, we use capital to be the random variable, the whole random variable, and we use lowercase to be the values that it takes. So the values that it would take would say be 1, 2, ... up to n. Okay, and so oh, sorry, maybe it should start with 0 because it could all be tails, right? And so yeah, so here, for example, with n equal 2, for 2 tosses of a coin, the value that x2 could take is 0. X2 could also take the value 2, and x2 could also take the value 1. So we say that x could take on the value 0, 1, or 2. So here this is the general case, right? And here this is the special case. Okay, so I mean that's what it means to be a random variable, right? So this x2 random variable, it might, if we actually do the experiment of tossing 2 coins, we might end up with a 0, we might end up with a 2, or we might end up with a 1. We don't know. the exact outcome. You toss 2 coins and you get a 0. A moment later, you toss 2 coins, you get a 2. A moment later, you toss 2 coins, you get a 1. You don't know what the value is, and so to hold that variable, we have this random variable kind of a thing. Okay? So we're going to be looking at these kinds of random variables actually for start out, and we'll look at this type. But consider this example where you say measure the speed of vehicles using like a radar gun, basically Doppler radar. So imagine the experiment that records the speed of cars that passes a Doppler radar. And so you've seen those signs that HPD kind of police department, right, puts up on the side of the road, and it shows your speed, right? And so as cars go by, you might suppose you're in hopefully a 25 zone, right? You see 29, maybe. And so you could think, hey, every time a car goes by, do we know what speed it's going to show? No, right? Why? Because cars go by at different speeds. So we could say that, x is a random variable, right? Because we look at the sign, but any time that a car is going by, we don't know what value it's going to show, right? And so, hey, it's random, right? And so, is there a difference between the xn from above, where xn is, say, the number of counts when you toss n, the number of heads when you toss a coin n times, versus y? So we're letting y be the random variable for the speeds, right? So, for example, the values of x would be 0, 1, 2, right? Some kind of an integer for the number of heads. Here, the values could be 49.9, could be 2.2, right? Probably not 100.0, could be, right? And so, is there a difference, right? Yes, right? There is a difference. And so, what is the difference between those two? What's the difference between the xn number of heads in tosses of a coin versus this y? So the difference is this idea about the difference between, say, discrete versus continuous. So discrete kind of means there's no in between. And continuous means that you could have, any value, including in-betweens. Okay, between values, so continuous. It's kind of like water, right? Except if you go to like the molecular level, where you might say, well, water really is discrete because we have discrete, in normal life, we would say that water is continuous because we cannot detect like the one water molecule, right? So water we would say is continuous, right? Versus, discrete. So you wouldn't have 2.5 heads, right? Or you wouldn't have like pi 3.141. You wouldn't have, if you're tossing, 3 or 4 coins, you would never have pi as the number of coins, right? Where somebody could actually be driving at pi miles per hour. It'd be really, really slow, right? 3.1 miles per hour, or 3.141, blah, 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 miles per hour. And so would be continuous speed. Okay? So what we want to get to, right, is this idea that we assign a probability distribution. So what we've done is now we have these events, we have these values, and so, hey, what's the likelihood of getting 2 heads? What's the likelihood of getting 1 head? what's the likelihood of seeing no heads, right? And so when we want to find these probabilities, that's where we actually have to drill back down to the events. And then once we have the events, we can figure out the probabilities, right? And then we can add them up. Does that make sense? So, what's the probability of that there's two heads? Well, we have to go back to the probability of what are the events. And so the events are that there's H followed by H. So what's the probability of HH? It's the number of heads divided by the total, and so that's 0.25. What's the probability? So there could be one head. So what's the probability? How likely is that? What's the probability of that? Well, you could have this one or that one, right? So, but they're mutual. If you have first one's heads, second one's tails, and then the first one's tails, second one head, that's mutually exclusive, right? You either got the first one is heads and the second one tails, or the first one is tails, second one head. That's it, right? So there's no intersection, so that's mutually exclusive, right? And so, furthermore, when you are tossing the coins, the first toss, each additional toss is independent from the next one, so that's how we can multiply. So this is where we use, in order to get these probabilities, we're actually using the ideas of mutually exclusive and independence. Okay, and so basically to get a 1 in two tosses of a coin, there's two cases, so that's kind of 2 out of 4, or which is a half or 0.5. And then finally, to get the no heads, it's how do you get no heads? Well, you flip two tails. So what's the probability of that? It's 1/4, and so it's actually 0.25. Okay, and so we actually assign, you can do it the direct way, you can do it sort of through independence and multiplying, you get the same way. Notice that it's possible to say, what happens if somehow you could have a coin that's biased, that it has a 0.6 likelihood of being heads, and then if it's 0.6, what's the probability of tails? Right, so for a fair coin, it would be a half. If the probability of heads is 0.6, what's the probability of tails? Right. 0.4, which is the same as 2/5, right? Which is actually 1 minus the probability of heads, right? So, 1 minus 0.6 is equal to 0.4, right? So you get either heads or tails. And so now it's possible to think about, where we're saying, even though we're going to talk about heads or tails, it could be, on time or not on time, right? It has a 0.6% chance of being on, 0.6 chance of being on time, and then it's got a 0.4 chance of being late, not on time, right? And so then you can actually work these out, and so you have a slightly different probability distribution, right? But here it's important to remember that everything sums to 1, right? So 0.25 is 0.5, that's 1. It turns out if you have this 0.36 and the 0.16 and the 0.48, they all sort of come up to 1. So the sum of these probabilities goes to 1, right? So the grand sum of all of these probabilities is equal to 1, right? Here's just so you look at it right now. We did 2 tosses of a coin. This is what 3 tosses of a coin looks like, right? And so here it could be the probability that there's 3 heads in a row. How likely is that? Here's how you would work it out. Say we're using the 0.6s. Now the probability of 2 heads. So you got the probability of 2 heads, and then one of the 3 probabilities is now this 0.4, right? 2/5 is 0.4, right? And so there's 3 cases of those, and so you add that up, and then where there's only 1 head, this is what it looks like, and then the probability that there's no head, And oh, by the way, this 0.1, 0.2, 0.216, 0.34, this probability and this probability, they all sum to 1. So if you sum up the probabilities, that equals 1. So we should have that 0.064 plus 0.28 plus 0.432 plus that other one, 216, 0.216. Those should all to 1. That's how you have a probability distribution. And sometimes people say, you know, what does it look like? So there's two views that we have of probability distributions. One is sort of the mass function, which is sort of like this kind of a view. And so here is, you know, 3 tosses with the 0.6. Here's the 2 tosses with the 0.6. And you can see it's kind of skewed a little bit more towards being heads because it's a little bit more likely to be heads. And then there's this other cumulative view. So these are both valid views of probability distributions. Okay, so we'll pick it up from here tomorrow. Oh yes. Okay, and I'll give you an extension. Do you have one? Do you have time?
Yeah.
Ask about it now. Okay.
Yeah. But I have my computer right now.
Okay. You want me to go over there?
Yeah.
Okay.